Okay, Assalamualaikum and good morning, everyone. So today we'll be continuing the lecture from last week. Okay, I think with lecture 10 of the notes. By the way, no, the numbering for each lecture doesn't mean correspond to any particular. It depends on how fast and slow I go in the lectures. Right, I think we have come at this particular stage where we have actually defined your four momenta here. So initially what we did was, just to recall back, initially what we did was to define your relativistic mass, okay, as something which is dependent on velocity. So this is mass as function of speed, really, not velocity, where the speed is essentially the speed of the frame, or could even be the speed of the particle itself, if you consider the proper frame. So in this particular case, then one actually, from the construction of the examples that we did, where we did a particle moving in the z direction, if I'm not mistaken. Let me just check. Right, okay, we have a particle sort of in collision in the z direction of each frame, and then the frame, one of the frame is moving relative to another, which is this particular frame moving the speed v, and by analyzing, by assumption of conservation of momenta first, and then analyzing the kind of mass that one can actually get, is that you find that the mass, the velocity dependent mass, will be given by the relativistic factor gamma here times the rest mass. Okay, so this is what I think we have done this, and then one can recheck that this formula actually works by resubstituting it into this equation of your conservation of momentum here. So that is essentially what we did over here. So we get to this point, okay. And finally, one can essentially write your ordinary momenta, but in this case with what we call the relativistic factor coming in. Okay, so essentially it looks almost the same like your definition of momenta in Newtonian mechanics, but the only difference is essentially this will be a velocity dependent mass. Okay, so and then this would be in terms of, your gamma is now been written out. Okay, and then this is your rest mass times the velocity of the particle. So one could also now put it into the definition of your, initially we posited the idea that the four momenta will be just your rest mass, which is considered to be an invariant in reference frames, okay, and then multiplied by the four velocity. In the four velocity, we have done this in the lectures before, and this will have this particular component for four velocity. Then essentially your gamma and your m naught will combine to be your mv, and then essentially you get relativistic momenta, which is looking like your ordinary momenta, and then this one will be what you call, we will relate this to energy in the next section. Okay, so we'll talk about this. So the idea is now what we have done essentially to use conservation of the three-dimensional momentum. Okay, but now one can actually imply, given that you have this formula for your four momenta, the four-dimensional momenta, the conservation of the three momenta here, okay, will imply that we'll have conservation of the four momenta. Okay, so this is what we're going to do next. So consider now two different vectors for which you have, so we are not talking about general arguments now. So you have four vectors. Remember your P mu is a four vector, right? So now we're considering a general condition where you have these four vectors given by A mu and B mu. And then to emulate the idea of conservation of the three momenta earlier, suppose now we put the condition that your three-dimensional version of your three-dimensional components of your A mu here and three-dimensional components of your B mu here is actually equal. Okay, and this should be with respect to a particular frame. But if you impose this condition to be true in any frames, then you see that the implication will be the equality of this A mu and B mu in all frames. Okay, so let's do this. So to consider the components of these vectors to be equal in other frames, then we have to write it how the each component transform. So you remember that the components are related by a Lorenz what you call Lorenz transformation. So this is your Lorenz matrix here. Okay. So but now you have to remember that we are concentrating on the three-dimensional components here. Okay. So you have I dash there. So you have your L now summing from getting the I dash, and then you have this other component. It should be something like this. Okay, maybe I should write it in full first. So this is essentially Li dash mu A mu. Okay, because there is no, this summation has to be there to begin with. Okay, so in other words, we'll have the summation on the three-dimensional part, and then of course also the fourth dimension. Okay, your four components here. Okay. Similarly, for your case of your vector B, then if this is the components in the dash frame, then it has to transform essentially with the undashed frame in this manner, just like the case of A. So this is Li dash say nu B nu. Okay, and now the condition that we had earlier, we say that if we want this to be true in all frames, then what would we have? First, we know that it's equal in one frame. Okay, so this is the I should say that we are subtracting all the dash components now, and that leads to this term minus this term. The auto admin is working. So so we have that difference coming in. Okay, and then essentially this is now equal. No, we made the first assumption to be the components are equal in one frame. Okay, and then that's going to be 0, and we are left with this term. Okay, and if you make the assumption that the spatial components are also equal in other frames. Okay, so initially we had the one frame first, and then you impose again the condition in all frames, then what's going to happen? Then you'll find that this has to be equals to that. So, and this now by imposition that this has to be equal to 0 if these are equal in all frames. Okay, then that will imply your A4 minus B4 has to be equal to 0. Or in other words, A4 must be equal to B4, or in general, what we'll have is essentially A mu equals to B mu. Okay, the condition here is to make this equality of the components, the spatial components, okay, the three-dimensional components of your A and B to be equal in all frames. If that is true, then that would imply the fourth component also be to be equal in all frames. Okay, so that tells us, okay, if we apply this to so now you can think of your, say, P mu initial, and then you have P mu final. Okay, then that will imply this equality will imply this equality. Okay, so which tells us, okay, the initial four momenta must be equal to the final four momenta. That implies essentially the conservation of your four momenta. Okay, so that is nice. So in other words, what we're gonna have is a extension of the law, the conservation law for your three momenta to the four momenta. Okay, this is provided, of course, the assumption here is you have the conservation of your three momenta to be true in all frames, meaning that okay, maybe I should write this thing down. So assumption is three momenta conserve, okay, in all frames. But what does that mean? That means in all frames, this implies in all frames the effective force acting on the system goes to 0. Okay, so then essentially then you have that conservation of three momenta to be true in all frames, and that implies further that you have conservation of the four momenta in all frames. Okay, so if we think what this is going to be, just check if okay, fine. If this conservation of the four momenta is true, then that would tell us, okay, this part of the component of your four momenta, okay, will be true in terms of the conservation law. So, but what does that tell us? That essentially tells us the conservation of relativistic mass, because y, your c, is just a constant, and then this will be just your relativistic mass. Okay, so let's apply this to the earlier example. Remember the earlier example, we had this mass, two particles with the same mass, the same rest mass, I should say, because one is actually moving, right? So, and then they coalesce to form a single particle of mass capital N. Okay, so what does the conservation of relativistic mass supposed to say in that particular case is to say that your m here, okay, has to be equals to the summation of the mass of the two particles. Okay, so in other words here, so we can actually remove c if we want to, but no, here we retain it because we want to show something else. Okay, so what is mi? mi is now given by the relativistic factor times the rest mass times c for each particle. So one of them might be already at rest, okay, but what the other particle will not be, okay. So in other words, we have this factor coming in, okay, and if you expand this part of the term, the square root under the denominator, one would be able to approximate it by a Taylor series. So essentially, you expand 1 minus v squared on c squared to the power of minus a half. Okay, so when you expand this, essentially that power will multiply with this to get your half m naught v squared on c. Okay, so that will be the first order term, and then you have the zero order term. It's just the constant c multiplied with the rest mass, and then you have the higher order terms. Okay, remember the first order term here is actually with respect to we are expanding with respect to v squared on c squared. So the higher order terms will be higher order terms of v squared on c squared. Okay, so and that tells us a very nice thing. If you look at this first order term, this is none other than your Newtonian kinetic energy divided by the constant c. Okay, so in other words, the conservation of your what you call relativistic mass implies in the limit where c tends to 0, which is the what we call the Newtonian limit, implies the conservation of kinetic energy. Okay, you see that the speed of the particle itself contributes in this relativistic mass. Okay, so that's why you have this. So you have this rest mass energy, and you add it with your Newtonian kinetic energy term, and then you have the higher order terms. Usually V is much less than C, which we can actually ignore. Okay, so that tells us this conservation of kinetic energy. Right, so now we want to define this in a much elegant way. So we are going to postulate the fact that the fourth component is now related to your kinetic energy, but it's not only just that. You have higher order terms of this expansion. Then let's posit the idea that your fourth component, your four momenta, is just simply what we call the relativistic energy, okay, divided by the constant c, because here you can see that this particular form is just your kinetic energy divided by c. Okay, so let's do that. So we posit this idea of relativistic energy, okay, which is now given in terms of your mass dependent velocity dependent mass, okay, times c. Okay, this is from your earlier definition. Remember here, okay. So you have this fourth component here, and then once you do that, one can rearrange this particular equation. So your E is now what we call the relativistic energy, and we bring the 1 over c factor to the other side. That will give you E equals to mc squared, which is the famous Einstein equation relating mass to energy. Okay, so this is your E equals to mc squared thing. Okay, so really this mass here is the mass that depends on the velocity. Okay, but if you take the case where v tends to 0, okay, you're looking at, say, the rest frame, then this relativistic mass energy tells us about what we call the rest energy. And normally in Newtonian mechanics, we don't have this idea. It's only coming from the point of view of relativistic mechanics. Okay. And then the other thing that one also have is the contraction of your P mu. Okay, earlier we had V mu equals to minus C squared. So what would be so this is what we call a Lorenz scalar. So Lorenz scalar doesn't change in when you change reference frames. So similarly, we can define this for your four momenta, okay, and then given that you already proceed, make the assumption that P mu equals to m what was it m gamma. Sorry, what am I doing? mv. mv. No, it's correct. Let me just check because I don't memorize things. Yeah, m not v mu. Sorry. So m not v mu. Then you can see that, okay, when you contract it with your, say, covariant vector here, then essentially that gives you the contraction with the covariant vector of the velocity, which tells you from previous lectures this is minus c squared. Then this gives you this what we call scalar for the case of contraction between the four momenta with itself. This is nice. This is constant in all reference frame. This is also constant in all reference. Okay. Okay. So let us expand your P mu here. Okay, in terms of the components. So you have your spatial components here contracted with your spatial components here, and then minus the fourth component times this fourth component. And that tells us what? That gives you the P squared, the three momenta square, and then the three momenta square summed all together gives you the magnitude square of your three momenta. And then the fourth component will just simply by our earlier postulate, which is saying the fourth momenta is just your relativistic energy divided by c. Then you get this p squared minus e squared on c squared. Okay, that is what I call writing out all the components in your P mu. Okay, and this is now equals to minus m naught squared c squared. So one has now this expression is equals to that. So on rearranging, then you get an expression for your relativistic energy to be equals to E squared equals to m naught squared c to the fourth plus p squared on p squared times c squared. Okay. So if you remember, I think you probably have seen this equation before in modern physics, which is now written as in a square root form. This is c squared. Yeah. Is this familiar to you guys? Okay. So in other words, what we have done is essentially our four-dimensional framework just reproduce what you know in modern physics. Okay. Now, it's not as easy as that. One has to also check what actually happens in certain special cases. In this particular case, let's check when your velocity of the frame goes to the speed of light. Okay, so in this particular case, then you'll see that over here, your three momenta, okay, is given by your velocity dependent mass, okay, times v, and velocity dependent mass has this relativistic factor over here, and you take c, v goes to c, then this term on the denominator is going to be 0, and that means this whole thing is just going to blow up, okay, to infinity. Same thing if we take the fourth component, which is now given by your relativistic energy divided by c, or you can write in this particular form. Okay, then you'll find that this also blows up, goes to infinity as v tends to c. So this, how can we make sense of this? If you have something that's moving relatively close to the speed of light, this quantities becomes infinite, which is essentially, I mean, it's when quantities become infinite, we say that that doesn't really, physically doesn't make sense. Then the only way that this can be avoided, okay, is to set your rest mass to be equal to 0. If you set your rest mass equal to 0, then what happened? This part of the equation is going to be gone, and then you have, okay, maybe I should say that later on. So the limit makes sense only when your rest mass equals to 0, or in other words, these things, no, well, I don't want to say goes to 0, but this thing might not be infinite. Okay, put it that way. That's the easier thing, because you have one going to infinite, one is going to 0. You have to see which one overcomes the other. Okay. So in the case of this zero mass, zero rest mass particle, which on the thing that we essentially deduce the limit where v tends to c, and v tends to c tells us, okay, this is essentially describing your photons, or in other words, whatever this particle is behaving like photons. Okay, so in other words, in this particular case, that implies that anything that can be accelerated to the speed of light has to have a zero mass. Okay, and photon, perhaps in what you call, in some sense, you have heard that your photons doesn't have mass. Okay, but it does have energy. So this is the sort of paradoxical kind of what you call statement, but essentially that's what that's how it behaves. Okay, in the relativistic sense, your energy is related to mass, despite your rest mass is not, your rest mass is 0, but you have the contribution of the velocity of the particle itself. So in this case, your photons doesn't go to rest; it's always moving with some velocity. So in this velocity is going to be the speed of light. Okay, so I hope that makes sense to you. So in other words, all this equation makes sense. Can all the paradoxical idea of this going to infinite will make sense when you set this m naught equals 0, and setting m naught equals 0 doesn't mean it doesn't have energy. It still have energy because we have the contribution coming from the velocity. Okay, so how can we actually write for this zero mass particles? How do we write in terms of the components and in a proper sense? Is to, okay, your velocity will now acquire the speed of light, and then so v equals to c in other words, and then being a vectorial quantity, there is a direction of the propagation of these particles or these photons. So you write as v equals to cn. So n will now be the propagation vector, and c gives you the magnitude. So this would be unit vector. Okay. And then your energy is now simply just written as Pc. Okay. So what's going to happen for zero mass particles, particularly for photons, you always your three-dimensional momenta, okay, your p of your momenta here as E over c times the propagation vector. Okay. So and this is the, as I said, this is a special case of zero mass particles. Okay. So your four momenta for your zero mass particles is now given in terms of this component. So this should be a the three-dimensional momenta. But your three-dimensional momenta is now defined as this. So I can have your E over C on N inserted here. But E over C is also appearing in the fourth component, so I can bring it up. So E over C is the common factor, and what's inside over here is your propagation vector, and then your essentially your scalar, okay, for your fourth component. Okay. And the other thing that one should also check is the Lorenz scalar, p mu. Previously we had this to be m naught squared c to the fourth, or m naught c squared. I can't remember now. I always forget all these things. Yeah, m naught squared c squared. Yeah. Okay. So what happens in the particular case? We have to make sure that this is also consistent. Well, your m naught is 0, so you expect this to be equal to 0. But let's check. If I have this four momenta, what's going to be the contraction? Well, the contraction is simply this is your magnitude, so you get your E squared on C squared magnitude, and then the contraction for your four-dimensional vector here, you have your magnitude of your unit vector n minus this constant 1, and that is simply equals to 0. Okay. So that works out. Okay. Even if you do not like this particular, it's like kind of assumption put into it, this particular aspect of the zero mass particle. Okay. Hope everyone is okay with entering the meeting. So that finally we have more or less considered this particular special case that also works when you write down in terms of the four momenta and four momenta, which includes the relativistic energy. Okay. Right. So as I've mentioned earlier, this is a topic on relativistic dynamics. So once you have done four momenta here and also your energy in some sense, then one should be finding some kind of an analog of your equation of motion in Newtonian mechanics. Okay. So again, just like your v mu, we have defined your four velocity as what was, I can't remember now. dx mu, d tau. Your tau is your proper time. Okay, and then p mu is essentially you can do the same. Well, you have your rest mass dv mu d tau. Sorry, that's not right. Sorry about that. V mu is dx mu d tau. P mu is m naught v mu. Okay. So our Newtonian equation is essentially F equals to, well, the familiar form is this, but one can actually consider a much more general version of this, because your mass now can actually change with time. So one should be dealing with this form of the equation, dp dt. So by this particular form of this equation of motion, one again try to define your four-dimensional version of your force as dp mu d tau in accordance to this particular form. Okay. Well, we have done p mu. We know that p mu is m naught v mu, and then d tau of v mu is just simply a mu. Okay, your four-dimensional acceleration. Okay, so, and one of the things that we know is that your four-dimensional acceleration is a space-like four vector. Okay, and the space-like four vector is always orthogonal to your time-like four vector. So you contract this, say, with the velocity four vector, and velocity four vector is a time-like vector, then you find that this is going to be equal to 0. Okay, because this is equal to 0. This, we have done this. Okay, so in other words, your f mu has to be orthogonal to your v mu. So now we have actually have not gone through what the components of this f mu is supposed to mean. So now we try to do that. So let's consider our v mu previously was given by your relativistic factor times your three-dimensional velocity here, and then your fourth component is just c. So if we just simply use this particular form, then this equation over here will give you this equation. So fi gamma vi coming from that, and then f4, the fourth component, which we have yet to see what it is. Okay, f4 times gamma times c. Okay, and adding up these two terms will actually give you 0. Okay, your fi vi, you can rewrite this as your fi is just your three-dimensional components of your force, and vi is your three-dimensional components of your velocity. So I write this as an f dot v here, and then f4 can now be written in terms of, when you rearrange this equation, f4 is just 1 over c times f dot v. Okay. Remember here, f is actually defined in terms of your proper time. So it's not really your Newtonian force that you actually see. So if we use your chain rule, okay, dp d tau equals to so we want dp dt. So this will be your ordinary force here. So this will be dt d tau. Okay, it's just chain rule, and dt d tau gives you gamma. Okay, so that's what we have to. So your Newtonian force is essentially this one, and we to differentiate between the relativistic force and the Newtonian force, we define this to be small f. Okay, so in other words, small f is your Newtonian force, just like in this particular case. Okay, and then your relativistic force is given by this Newtonian force, but modified by this relativistic factor, which is again a quite good thing, because this you always get the analog equation in relativity modified by this factor. So that settles essentially your three-dimensional components. Now that leaves us with the fourth component, for which we need to find out what does it really say. Okay, what physically does it mean for this fourth component? Well, we have seen that this is equal to that. Okay, your fourth component is equal to this. So substitute your capital F equals to gamma F, small f. So I will have 1 over C there, gamma F, okay, and then dotted with V. And this is essentially gamma dp4 dt from, where was it? Well, I mean, is your P4 is, remember that we had this, okay. Your P mu will now be, sorry, your F mu, F mu is the P mu theta, right? So now we are just concerned with our fourth component. So you have the fourth component of this, which now translates to this, okay, and the fourth component F4 is from this equation here, gives you this. And if you look what this is, your fourth component or P mu is just E over C. Okay. So now what we essentially have, this dp4 dt is now becomes 1 over C dE dt. Okay. And 1 over C dE dt is essentially the rate of energy change over time. Okay. And which is related to this F dot V, which is something that we already know. F dot V, if you remember, F dot S in Newtonian mechanics is essentially your work done, or in terms of this would be delta E. Okay, so this is going back to a very basic cause of Newtonian mechanics. So if you put d dt of this, then you essentially have rate of change of energy. And this is precisely what we have for the fourth component. Okay, so everything in the end makes sense. The only thing that, we just need to find out what this fourth component actually means, and we know now that this is essentially your rate of change of energy. Okay, I think that's about it for this particular lecture. Let me see if there's anything more under this. Oh, there's a bit more. Right, okay, so so now essentially we can write this for your three-dimensional momenta, three-dimensional force, and this is the three-dimensional relativistic force given by dp dt, and this is actually dp d tau here, but this can be written as that. Okay, so let's try to see how this equation actually works. Let's consider the case of the simple case of motion in one dimension. So there's only one component of your space. So that equation earlier will translate to this. Okay, this is your gamma times V. M naught is a constant, you can bring it outside. So I get V over square root 1 minus V squared on C squared, being differentiated with respect to time. Okay, so now remember your V here, unlike the case that we have treated earlier, where we think of your velocity of the frame. The velocity of the frame is not accelerating. Here it can be accelerating because we're talking about dynamics here. Okay, so in other words, we have to be careful when you take the time derivative here. The time derivative not only works on this term but also works on the operates on the denominator. So we need to do both. So let's do that. So this is just the differentiation of your v, and then the next one that we need to differentiate, you leave v, you differentiate that, and this gives you all this slightly more complicated looking calculation here, but I'm sure you can actually do that. You just differentiate d dt of 1 minus v squared on c squared to the power minus a half. So you take minus a half to the front, okay, and then you take the derivative inside, and then that leads to that. So you can see that in both terms over here, you have the common term dv dt. You can bring it outside. Okay. Also, you have a common term of the square root here. So here it has to the power of 3 over 2 is which you can bring up part of it out. So you get 1 over square root 1 minus v squared on c squared times dv dt. And then this one becomes 1, and this one becomes v squared on c squared divided by 1 minus v squared on c squared. So you can actually try to simplify this, and in the end you get this one, which cancels out the v squared on c squared there on top, and you are left with this term. Okay. So why are we doing this? Well, it says what? It says if you, okay, this is going to be equals to f, right? Now, I can invert this to get a formula for dv dt. Okay, dv dt is how much you can accelerate your particle, or in this case, any object, even a frame. So dv dt is given by f over m times 1 minus v squared on c squared to the power of 3 over 2. Just rearranging this equation. Okay. And this term is going to be less than 1. Okay, because your v is always less or equals, okay, in the case of a zero mass, v is less than c. So this is less than 1. So the whole thing must be less than f over m. Okay. So in other words, what we have is that this force in relativity will not be able to accelerate beyond certain limit. Okay. So if you look at what happens when v goes to c, when v goes to c, this tends to 0. Okay. So you can, when it reaches this particular limit, you cannot really accelerate it anymore. Okay. Despite that your force is actually non-zero, even in the case of a non-zero case, then you find that this term is going to go to 0 faster. Okay. So then what's going to be is, the implication is to say that you cannot really accelerate a massive particle to the speed c. Okay. So that is quite interesting because you can see, for example, in the particle accelerators, they will never achieve say accelerate say a proton or electron, the accelerator. It will never achieve the speed c, but it can come quite close to c. So this has been shown in in the labs of the say the collider experiments, for example. Okay. So this has actually an implication, and if you really want to accelerate a particle into speed c, the only way that you can actually do that is to make the particle to be massless. There's no other way. Okay. So that's a very nice implication of relativistic dynamics. I still have a bit more here. Okay, probably we have to continue this tomorrow because this will now it's already 4 minutes to 9. So let me just go to your page here. By the way, your test one I should be marking sometime soon. I just don't have the time at the moment. Your result should be at earliest will be this weekend. Okay, so let me get your attendance. Okay, so that's it for today. So any immediate questions at this stage? I guess. Okay. So thank you everyone. So shall now see you tomorrow. Okay.
Okay.
Bye.